All right, so we have two inputs in this system and two outputs. So there are going to be 4 transfer functions, 4 frequency response functions. Our system can be written in matrix form. All right, the system can be written in matrix form. As x dot is equal to ax plus b u. Our inputs here are u1 and u2. They're just some generic inputs. We don't know exactly what they are, but there's some input. And then for the output, we're going to get y is equal to cx plus du. And these matrices you can pull from the equations that were given above. So just to remind you, the transfer function matrix G of s. This relates y of s to the input, or more specifically, y of s is equal to G of s times u, big U of s, and what you guys are going to do now is you're going to go compute this transfer function, the 4 transfer functions, and then you're going to convert those into an FRF, into the FRF matrix where we set s equals to j omega. You guys will work on this, and then after some time I'll come walk around during that, and then I'll come and solve it up here. Okay, so just as a brief note, the Ogata book uses the term sinusoidal transfer function instead of the word frequency response function or the term frequency response function. These are the same thing. So there's not really a difference. The frequency response function really comes from the vibrations world. Honestly, I have no idea where you would see sinusoidal transfer function. I've never seen that before until this book. So I don't know. All right, so we're just going to use the word FRF, but when you read the textbook, or if you read the textbook and you see sinusoidal transfer function, it's the same thing. All right, so the FRF system may be represented by 2 separate plots. First is the plot of the magnitude. The plot of the magnitude versus frequency, or the amplitude versus frequency. And the second is a plot of the phase versus the frequency. Which is what we've seen before when we plotted FRFs and we plotted the magnitude, and we've also seen the phase of the response. Okay, so another useful way to represent the frequency response characteristics of some system is using what we call a Bode diagram. A Bode diagram is very similar to what we've seen before. The only difference is that we're now going to put we're going to switch the magnitude into decibel scale, and we're going to put frequency on a log scale as well. So the Bode diagram is going to consist of 2 things. First is a curve of the log magnitude versus frequency, or versus log frequency. And then the second is a curve of the phase angle versus frequency versus log frequency. So like I mentioned, we're going to use a decibel scale for our y-axis here. So the standard representation of this log magnitude is using decibel scale, where we're going to plot 20 times the log base 10 of the magnitude of our frequency response function. And again, we're using base 10 here, and the units are in dB or decibels. And in this representation, the frequency is going to be set to a log scale, while the magnitude and the phase are both linear. The magnitude is linear, but on the decibel scale, which we're going to talk a bit about. And the phase is just linear in degrees, or radians if you want. All right, so the main advantage of using a Bode diagram is that the multiplication of magnitudes or different components in a transfer function, that multiplication can be converted into an addition. And this allows us to simply add things together when we're trying to plot a Bode diagram. It ultimately allows us to plot the frequency response function, both its magnitude and phase, without having to actually go and compute that analytically. We can just do that using asymptotic approximations, which is what we'll see when we deal with first order systems. So the fact that multiplication converts into addition is one of the things that allows us to do this. And then the second thing is that we can sketch approximate curves that give us basic insight into what's going on. And as a result, if we have some frequency response data, we can then do an experimental determination of the transfer function from our Bode diagram. And so we'll do an example where one example we'll go and draw the Bode diagram for a system, or we'll estimate it based on the transfer function, and then we'll do the inverse where we're given a Bode diagram and we can go in and compute or estimate the transfer function from that. Okay. The reason we put log or the frequency on log scale is because it now allows us to see both low and high frequency stuff. And this is particularly important because generally low frequency behavior is of concern in practice for dynamical systems. In vibrating structures, low frequencies have high amplitudes, which can lead to things breaking if they're too high. And so low frequency is a concern there as well. Yeah, so like I said, characteristics at low frequencies are the most important, so expanding this into a log scale and allowing us to see that at low frequencies is very important. Okay, so the book includes what it calls the number decimal conversion line. This is just a line that allows you to convert a number to its corresponding decibel value. You can also just use a calculator to do that. It's not really a hard thing to do, but the book does include this in case you wanted to use something like this. The key thing is that as a number increases by a factor of 10, its decibel value will increase by 20. And we can see this by taking some number k, computing its decimal value, we'll say 20 times log of the number k times a factor of 10 raised to the nth power. If you go and compute this, you'll find that this ends up being 20 times the log of k plus 20 times n. Such that indeed increasing a number by a factor of 10 will increase its decibel value by 20. Or if you decrease the number by a factor of 10, you'll decrease its decibel value by 20. All right, so then the reciprocal of a number in decibels differs from its value only in sign, meaning that if we take 20 log of k, this is going to be equal to the negative minus 20 log of 1 over k. All right, we're going to talk about different components that you would see in a transfer function, such as just a constant value, a derivative or an integral term, and then we'll look at a first order system, meaning a first order differential equation. Okay, so for a constant value, which you'll often hear called a gain, so for a number larger than unity, it's going to have a positive value in decibels, while any number smaller than unity is going to have a negative value in decibels. Okay, so the log magnitude of a constant, such as a gain k, is simply a horizontal straight line, and it has no dependence on frequency. Additionally, the phase angle is 0. And so we can multiply our transfer function by any gain k, and this is just going to have the effect of shifting the magnitude vertically in our Bode diagram, either increasing the magnitude or decreasing it directly. It will not change the phase though. All right, so just as an example, if we want to vary some gain or some constant in a transfer function, such as in h of omega equal to some big fraction, we'll have capital K times quantity j omega plus z0, that's our first zero, plus, or actually multiplied by j omega plus z1, the second zero, dot, 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 then multiplied by j omega plus some zm for the mth zero. And then in the denominator, we're going to have j omega plus p0 times j omega plus p1, dot, 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 j omega plus pn for our nth pole. In this case, this constant k is what we call the gain, and it simply is going to raise or lower the log magnitude by the corresponding constant amount without changing the phase. Okay, we're talking now about what happens when you have a derivative term or an integration term. So derivatives have the effect of multiplying your transfer function by j omega, while an integral will have the effect of dividing by j omega. So we're going to start by computing the log magnitude of 1 over j omega. In this case, this is going to be 20 times the log the absolute value of 1 over j omega. These are all log 10, log base 10. This is then equal to minus 20 times log omega in dB. And then the phase angle for one of these integral terms is constant, and it's going to be equal to minus 90 degrees. So what we find is that the log magnitude plot of an integral term is just a straight line with a slope of minus 20 dB per decade, which is what we can see to the kind of bottom left here. That is the Bode diagram for an integration term or integral term, which is just 1 over j omega. To the right of that, we have the corresponding curve for a derivative term, which we're going to write out right now. So log magnitude of a derivative term is going to be 20 times log, it's the absolute value of j omega, and this is simply going to end up being equal to 20 times the log of omega in dB. So in this case, it's now just a positive straight line with a slope of 20 dB per decade. In this case, for a derivative term, the phase angle is 90 degrees and is also constant. All right. We shall go on to looking at a Bode diagram of a first order system. Next week we'll deal with second order systems. We're going to consider the first order system capital T times T dot or times X dot plus X is equal to some input F of T. This first order system is going to have a transfer function of G of S equal to 1 divided by Ts plus 1 and an F or F of H of omega equal to 1 divided by T times J omega plus 1. All right, we can go and compute the log magnitude of this F or F. It's going to be 20 times the log of the magnitude of 1 divided by T, J omega plus 1. This will be equivalent to minus 20 times the log of the square root of omega squared times T squared plus 1. Square root of all that. All of that in dB. Okay, using this expression, we can now look at some asymptotic expressions and do some approximations. So first, at low frequencies, which is omega is much, much less than 1 over t, we can approximate the expression above as minus 20 times the log of the square root of omega squared t squared plus 1. We can approximate this as minus 20 times the log. In this case, because omega is much, much less than 1 over t, the first term under the square root is going to be very, very small. And as a result, we can neglect it, leaving only a 1 here. So we'll get minus 20 times the log of 1, which is equal to 0 dB. Such that at low frequencies, our Bode diagram is just going to be a constant line of 0 dB. All right, we're going to now ask what happens at high frequencies when omega is much, much greater than 1 over t. In this case, this expression is going to be approximated as minus 20 times log square root of omega squared t squared plus 1. In this case, with omega being very large, the first term is going to dominate the expression such that this plus 1 really doesn't add anything, and we can end up neglecting that term. And we'll end up finding that this is going to be approximately equal to minus 20 times the log of omega t in dB, such that it is a straight line with a slope of minus 20 dB per decade, true for omega much greater than 1 over t. All right, so the point of this analysis is it shows us that we can approximate our log magnitude of our FRF as a straight line with 0 dB for omega greater than 0 but less than 1 over t, and then we can use a straight line with a slope of minus 20 dB per decade for omega greater than 1 over t. Okay, so the frequency 1 over t is what we call the corner frequency. This is, or also known as the break frequency, but we'll use corner frequency. This frequency effectively divides the FRF curve into two different regions. The first one is where it can be approximated asymptotically as just a straight line, just as a horizontal constant. And then the second region is where we can approximate it as a vertical line or as a horizontal line with a slope of minus 20 dB per decade. Okay, so if you're given a transfer function, what you can do is you can determine what the corner frequency is. And once you know this corner frequency, if it's a first order system, you can use that to determine what this Bode, what the magnitude plot is going to look like. All right, we're going to take a look at the phase angle here. The exact phase angle for this system is equal to, phi is equal to minus the inverse tangent of omega t. We're not really going to be able to do any asymptotics here, so we're just going to have to recognize what happens at the corner frequency. So first, at 0 frequency, the phase angle is going to be 0. And then at the corner frequency, the phase angle will be, phi will be equal to minus the inverse tangent of t over t, which is just equal to the minus the inverse tangent of 1, which is then equal to minus 45 degrees, and that's our equation 22. And then lastly, as omega approaches infinity, the phase is going to continue down until it reaches 90 degrees. And so in the Bode diagram, we are plotting both our magnitude and our phase together. You can either put them in one single graph. Often they're split off into two graphs separately, but reported together at the same time. For the phase, for the magnitude, we can use asymptotics in order to approximate what's going on and figure out roughly what the magnitude will look like. For the phase, we need to recognize what happens at these corner frequencies and then go from there. Okay, so using the asymptotes, the approximate error in the magnitude is maximum at the corner frequency, meaning that if we just approximate our magnitude plot using this asymptote and this asymptote, we're going to have the maximum error at our corner frequency, and that error is minus 3 dB. And as a result of this, we can get a pretty accurate estimation of what's going on. At least roughly, we can get a rough estimation of what's going on using the asymptotic approach. So if you're in a situation where you need to very quickly compute what this looks like, in real time, using this asymptotic approach is what you should do. It will save you a ton of time. Okay, so note that varying the time constant capital T, is going to shift our corner frequency to the left or the right, depending on whether we decrease it or we increase it, but the shapes of the curve are going to remain the same. And another thing to note is that this first order system, or a system that has a frequency response of 1 over t times j omega plus 1, has a characteristic of a low pass filter, in the sense that it's going to suppress things at high frequencies. If we go back up to our magnitude plot, we get something that is very close to 1 dB or 0 dB for low frequencies, and then it drops off steeply for higher frequencies. Okay, we're going to go through our example 4 here. We are given the following differential equation, and then we're asked to plot the Bode diagram for it. That equation is 3x dot plus 4 is equal to some generic input f of t. We're going to first compute the FRF. We're going to do that by taking this Laplace transform, 3x dot plus 4. This is equal to the Laplace transform of f of t. This is going to give us 3s plus 4 times big X of s is equal to big F of s. From here, we're going to find that our transfer function g of s is equal to 1 divided by 3s plus 4, such that the FRF, or h of omega, this will be equal to 1 divided by 3 j omega plus 4.
Just to check my understanding, when you took the Laplace of 3x dot plus 4, where does the x of s come from for the 4 component? I thought you would have gotten 3s plus 4 in parentheses.
Oh, I'm sorry. There's a mistake here. This should be 4x.
Okay.
Yeah, that's what it should be.
Maybe I was confused for a second.
Yeah, no problem. All right, so our goal now is to place this into the form h of omega is equal to some a divided by t times j omega plus 1. And then once we put it into this form, we'll then be able to compute the Bode, or plot the Bode diagram.